Okay, so last time we talked about this strange algebraic definition of the determinant in terms of a sum of products of numbers that are pulled out of the matrix in little groups so that you get one from each row and one from each column each time. Now I'm going to talk about the geometric understanding of what determinants are. So suppose we have the matrix 3, 5, 4, 1. Okay. We can actually think of a matrix as defining a function. And so say x is a vector, and I have a function f which sends the vector x to some other vector y. Okay, and I'm going to define what f does to the vector x by saying multiply it by a. Okay. So then I could say, let's look at the standard unit basis vectors. So here's the, wow, that was weird. Here's the point 1, 0, and here's the point 0, 1. Okay, so let's look at f of 1, 0. Well, f of 1, 0 gets mapped to a times 1, 0, or 3, 4, 5, 1 times 1, 0, which is 3, 4. It just takes the first column of a. All right. And f of 0, 1 is going to similarly be 3, 5, 4, 1 times 0, 1, which is going to be 5, 1, the second column vector of A. So let's just make a note of that. And so let me now go to this picture where I've sketched what it looks like. So in the blue here down at the bottom, these are the input vectors right here. That's my 1, 0 and my 0, 1 vectors. And then when I feed them into the function, this first one gets mapped out to 3, 4, and the other one gets mapped over here to 5, 1. All right. So what that has the effect of doing then is transforming that blue square into this giant orange parallelogram. And so the determinant of A turns out to be the scaling factor of the area, the measure of that region in the transformation. So this is going to be, so the determinant of A, so 3, 5, 4, 1. Now you notice that these are straight bars. They're not brackets. And that's because we're talking about a determinant. So this is not a matrix I just drew, it's the determinant of a matrix, so it's actually just a number. And it's equal to 3 times 1 minus 4 times 5, which is minus 17. And so the size of the orange, the area, that is, of this orange guy here, this is 17 times bigger than the blue square. So the area of the orange is 17 times the area of the blue. And then you say, wait a minute, why is there a minus sign back over here? It doesn't make sense to talk about a negative area, and that's true. The negative sign does not correspond to the area. The negative sign corresponds to the orientation. So suppose, let's look at, let me recolor the little vectors that I started with, and I'll have this one be green and this one be red, And then we've got that the green gets mapped to the green and the red gets mapped to the red. Now, watch what happens if I look at a path that goes around the little blue square, starting by going down the green and going all the way around. Okay, so it's going counterclockwise. And now if I look at the orange square and I have a path that goes from the origin starting going down the green and going all the way around, you notice, oh, during that transformation, when the square got rotated, stretched, squeezed, and elongated out into that parallelogram, it also got flipped. And now the orientation is different. And that's the meaning of this negative sign right here. The orientation has changed. And now this whole thing also works in 3 dimensions. So if you start by looking at the little unit cube here in R3, and then you multiply all of the vectors in that little unit cube by some matrix A. Oh, I just realized I'm writing in a thick pen here. Multiply all those vectors by A, and it's going to end up being some who knows what looking parallelogram. So we've got something that looks like this. And the determinant of A will be the volume change factor now between this guy here, which has volume 1, and this guy here, which has volume, well, I didn't work out a numerical example for this one, but it looks something like the determinant of A in this case might be like maybe 3, something like that.